Okay, so I want to go through an example of computing the SVD, and so I'm going to take an example that is going to be quite simple to begin with, just to show you how things work. So I'm going to take the matrix 1, 1, 0 and 0, 0, 1. And I want the SVD. Okay, so first thing we need to do is compute A transpose A. So A transpose is the matrix 1, 1, 0, 0, 0, 1 times the matrix A 1, 1, 0, 0, 0, 1. So this is A transpose A, that is equal to, okay, so I'm expecting here this is 3 by 2 times 2 by 3. I want a 3 by 3 matrix, okay? So first do these and these. So 1 times 0 is 1. 1 times 1 is 1, plus 0 times 1. 1 times 1 plus 0. And 1 times 0 plus this. A second row, I get a 1. I get a 1 and a 0. And last row, I get 1 times 0 plus 0 times 1 is 0. 1 times 0 plus 0 times 1 is 0. And 0 times 0 plus 1 times 1 is 1. So that's my matrix A transpose times A. Now, second step, compute the eigenvalues and eigenvectors later, but of A transpose A. So let's get started. Here I want to point out a little trick that might be very useful to you. So when you look at the matrix A, you see that A transpose A, sorry. A transpose A, I'm going to write it out by spreading things quite well. So 1, 1, 0, 0, 0, 1. So when I look at this matrix, I see that it's what's called a block diagonal matrix. Why is this? So let me change color just to illustrate this. So if I were to take my pen and cut through this matrix, I would see that I have a matrix that has diagonal blocks. Let's say D1 equal to 1, 1, 1, 1. And D2 equal to just the scalar 1. Okay, the off-diagonal blocks, they're not square, but they consist only of zeros. So I have diagonal square blocks and 0 blocks elsewhere. So if you remember what was happening when you were looking at, let me change color again. I don't know, let's do it blue. So if I have a matrix, and this is a remark that I made earlier in the course, if I have a matrix that is a diagonal matrix with entries D11, D22, Dnn, then the determinant of D is the product from I is 1 to n of dii, okay? And the inverse, provided the determinant of D is non-zero, the inverse of D is simply the matrix with the inverses on the diagonal. 1 over D1, 1, 1 over D2, 2, so on and so forth, up to 1 over Dnn. Well, block matrices work exactly the same way. If my matrix, instead of being just a diagonal matrix, it is what we call a block diagonal matrix. And so this we will write typically in a weird form. So that would be the matrix D11 plus, with a circle around it, a matrix D22 plus, and so on and so forth, D, let's say K. Then exactly the same way as the determinant of the matrix was the determinant of the product of the diagonal entries. Here we would get the same thing. So except that here the determinant is going to be, the determinant of D is the product, again, from I is 1 to K this time, I have K blocks here, of the determinants of the DII. Okay, these matrices, the diagonal blocks for DII, they don't need to be diagonal. Okay, they can be anything. They need to be square, but besides being square, they can be anything. But instead, this means that instead of going through the whole computation, you can go through the computation for each block and just multiply through. And the same thing is true as we had before. If the determinant of D is non-zero, then D inverse is simply D11 inverse. Oops, that's a very ugly inverse. So it's the diagonal matrix, block diagonal matrix, which has diagonal blocks inverted from the original diagonal blocks. So if I go back to my original problem here, and diagonal blocks are, determinants and diagonal blocks, they are the same, they work the same way for eigenvalues. So the eigenvalues of the matrix A transpose A here are the same eigenvalues. So let's continue now to the where we were. So our matrix A transpose A has the same eigenvalues as the matrices. So the first, what did I call them? D1? Yes, as the matrices D1 and D2. So you see, instead of having to compute the determinant of a 3×3 matrix, here, because of this diagonal structure, I just need to compute. So we have, we find, what do we find? We find that the first D2, that's the sort of archetype of the simplest possible diagonal matrix. It's a scalar. D2 has the eigenvalue 1. Okay, because if I look at this scalar equation, I'm looking for solutions of A lambda V, AV equals lambda V, or I'm looking for D2 minus lambda times identity, but identity in the 1-1 case is just 1, okay? So if I, let me write it like this. V equals 0, okay, for a V non-zero. And remember that this is equivalent to solving the polynomial P of lambda equals determinant of d2 minus lambda times identity for 1. So identity 1 is just 1, okay? This equals 0, which means that lambda equals d2 equals 1. Okay, now for the eigenvalues of the first block in the matrix, so D1, remember, is just the matrix with ones everywhere. So here the same. I want to solve a polynomial P of lambda given by the determinant of D1 minus lambda times identity. Here I'll just indicate it's the identity of size 2, of course. So this is 1, 1, 1, 1. The determinant of this minus lambda times 1, 0, 0, 1. And that is the determinant of 1 minus lambda, 1, 1, 1 minus lambda. Okay, so let's compute this determinant. We'll continue the computation. P of lambda is the, so what do I get? What is this determinant? It's 1 minus lambda squared. Minus 1. So this is lambda squared minus 2 lambda plus 1 minus 1. So this is lambda times lambda minus 2. So eigenvalues, so I find lambda equals 0 and lambda equals 2. So the eigenvalues of A, transpose A, are 2, 1, and 0. And notice that I've already ordered them as they should be, because if you recall, once we have the eigenvalues, we want to order them in the same, in decreasing order. So from this, we deduce that sigma 1 is equal to square root 2, sigma 2 is equal to 1, and sigma 3 is equal to 0. Okay, so we have our eigenvalues, the corresponding singular values. Let me point out these are the singular values. Now we need to compute the eigenvectors associated to the eigenvalues, and these will constitute the matrix V. Okay, so eigenvector, and remember we said we have to compute them in the same order as the eigenvalues, and the eigenvalues are in decreasing order. So the eigenvector associated to lambda equals 2. What do I need to do? I need to solve. I need to find V1 non-zero such that, so I can write it either as the linear system A V equals lambda V, or I can write it as A minus lambda times I times V equals 0. So let's do the latter. It doesn't really matter. So A minus lambda I V1 equals 0. This is equivalent to saying that A, so I should A transpose A. Okay. I'm computing the eigenvalues of the eigenvectors of A transpose A. I'm so used to writing a V. Okay, so A transpose A. So that matrix is 1, 1, 0, 1, 1, oops, 1, 1, 0, 0, 0, 1. And let's put a parentheses here. Minus lambda is 2 here, 2 times the identity. This times v, 1 equals 0, 0, 0. Sorry, I'm getting to the end of the page. Okay, so let's compute what that is. So this is 1 minus 2 is minus 1. Second entry doesn't change, and the third entry was a 0. 1 and 1 minus 2 is again minus 1. And 0, so that's a minus 1. So I am looking to solve this, and let's call this, how should I call it? V1, 1, V1, 2. This is a little stupid as a way of writing it, but this is the first, second, and third component of V, or maybe let's change and just put them like this, just so it's clear that I'm not looking at matrix entries. And I want to solve this equals 0. So that's where, okay, I'll use this as a slight reminder of what happens when you're looking for eigenvalues. Of course, here the obvious solution, the trivial solution works, okay? So if I were to put V1, 1, V1, 2, and V1, 3 equals 0, 0, and 0, that would work, but that is not what I'm after. So what we do find is that, so I'm looking for a non-zero vector. The third component is obviously 0. Okay, V1, 3, if you look at this, the third component, we get that minus V1, 3 is equal to 0, is V1, 3 is equal to 0. For the other two, what do we get? We get that minus, how can we do? Well, for instance, we would take, well, let's write the system as it is. So we get that minus V1, 1 plus V1, 2 equal to 0, and V1, 1, I'm doing things, no, that's good. V1, 1 minus V1, 2 equals 0. Okay, I've put the third equation first because I already know what it is. And so what we get is that V1 is equal to minus V2. Oops, V1, 2. And of course, V1, 3 is equal to 0. So that means that an eigenvector is simply something of the form, so I'll call it V1. Remember, V1 is a vector, is a vector of the form 1, minus 1, 0. Oh, sorry, I've got a sign change. My gosh. Okay, look at these two equations here. What this says is not plus, minus, it equals plus. I'm an idiot. Okay, so this is plus. Okay, that's what V1 is. Always check your computations. You're likely to make mistakes if you're like me. Okay, maybe I won't do all the computations right away. Let me just point out, we find V2, has looks something like this, 0, 0, 1. And V3 is actually what we were getting beforehand, is minus 1, 1, 0. And notice, just in passing, when we got to this equation, I picked values arbitrarily. Of course, I did not pick 0 because that would be contrary to what we're trying to do with the eigenvector, but otherwise I picked the simplest value, which was 1. Okay. Now, all these values are different, so from the theorem we saw a little earlier, we know that all these eigenvectors are orthogonal. Okay, and you could check this very quickly. For example, if you take v1 dot v2, well, that is v1 was 1, 1, 0 dot v2, which was 0, 0, 1. And you can easily see that 1 times 0 plus 1 times 0 plus 0 times 1 is equal to 0. But we know the vectors, the eigenvectors. I'll often write E vectors for eigenvectors. Okay, we know that the eigenvectors are orthogonal, which we often write like this, by, I believe it was theorem 5, but let's say by a theorem in the notes. So we know these vectors are orthogonal. We want to make them into an orthogonal matrix, which I remind you has the additional property that the columns form an orthonormal set. So we take to make V an orthogonal matrix, we need that the set V1, V2, V3 be orthonormal, or normal. Okay, so we take V1 is equal to, well, norm of V1. Norm of V1 is square root of 1 squared plus 1 squared. So we take the new V1, V1 equals to 1 over square root 2 times 1, 1, 0. That is the vector, that is 1 over square root 2, 1 over square root 2, 0. Norm of V2 is 1. So we take V2 equal to what we had already found. 1, 1, 0, 0, 1. This 1 is... Don't know why my pen is being a little fussy that way. And finally, V3 has a norm square root of 1 minus 1 squared plus 1 squared plus 0. So it's also got a norm equal to square root 2. So that means that in the matrix V, we'll be using V3 equal to minus 1 over square root 2, 1 over square root 2, 0. Is that correct? Yes. Okay, so V is equal to these vectors, the matrix where we take these vectors as columns. So 1 over square root 2, 1 over square root 2, 0. 0, 0, 1, and minus 1 over square root 2, 1 over square root 2, 0. So that's my V. Let us now compute, while we're at it, let's compute, let's set up, there's no computation involved here, the matrix sigma. For sigma, and just to emphasize that it's not just the sum, it's just the capital letter sigma. For sigma, what we need to do is we take the matrix that has the same dimension as A. Okay, remember, if A is Mn, the matrix sigma is Mn as well. And it has a block that has the non-zero singular values. So the matrix D has the singular values that are non-zero, so that's square root 2 and 1. And we pad that with zeros in order to get a matrix of the same size as A. And in our case, A has 3 columns and 2 rows. So sigma is the matrix square root 2, 0, 0, 1, 0, 0. And finally, recall that the matrix U, we're, so for U, for the UI, we use UI equal 1 over sigma I, when we're not considering the 0 singular values. Okay, so this is 1 over sigma I times A VI. And I'll say I equals 1, 2. We do not consider sigma 3 equals 0. So let us consider now U1 first. Okay, U1 is 1 over sigma 1 times A, not A transpose A. Okay, so this is 1, 1, 0, 0, 0, 1 times the vector V1, which is 1 over square root 2, 1 over square root 2, 0. Sorry, I forgot to replace sigma 1. Sigma 1 was square root 2, so this is 1 over square root 2. To simplify my life, why don't I carry through this multiplication first? So this is 1, 1, 0, 0, 0, 1, a half, 0. Okay, so let me move this. So what does that give me? That gives me a half and a half is 1, and the second row is 0. Okay, that's U1. U2 is equal to 1 over sigma 2, and sigma 2 was 1 if I remember well, but where am I? Yes, sigma 2 is 1. So this is 1 over 1. Useful. 1, 1, 0, 0, 0, 1 times the vector V2, and V2 was... Have I lost V2? What did I do? V2. V2 and 0, 0, 1. Okay, and that gives me 0, 1. Now, recall that the matrix U must also be orthogonal, so the U1, U2 must form an orthonormal set, but here it turns out that quite clearly U1 and U2 are of norm 1. So let's just say U1, U2 of a normal set, since normal view 1 equals normal view 2 equals 1. But do check this every time. Normally, very often it will be that way, but I am not entirely sure if it will be this way over time, so just make sure. So that means that the matrix U is 1, 0, 0, 1. Okay, and so we have it. So the singular value decomposition of A equal to 1, 1, 0, 0, 0, 1 is A equal U sigma V transpose with U equal to 1, 0, 0, 1. And that is indeed an orthogonal matrix. Sigma equal to, what was sigma? Where have I put sigma? Square root 2, 0, 0, 0, 1, 0. What did I say? Square root 2, 0, 0, 0, 1, 0. And V, it doesn't matter whether you put V transpose or V. Let's just say V equal to 1 over square root 2, 1 over square root 2, 0, 0, 0, 1, minus 1, oops, minus 1 over square root 2, 1 over square root 2, 0. And that is it.